Dear students, today I am going to discuss our topic deadlocks with you. That is the basic definition and the system model. Firstly, we should know what is deadlock. Deadlock is a situation in which two processes sharing the same set of resources are effectively preventing each other from accessing the resource, resulting in both programs ceasing to function. The earliest computer operating system ran only one program at a time. All of the resources of the system were available to this one program. Later on, operating system with multi-programming support ran multiple programs at once, interleaving them. Programs were required to specify in advance what resources they needed so that they could avoid conflicts with other programs running at the same time. For example, we have a system with two disk drives. The process P1 and P2 each hold one disk drive and each needs another one. For example, two trains approaches each other at crossing. Both will come to full stop and neither shall start until other has gone. By taking this example, we can see if traffic is in only in one direction, each section of a bridge can be viewed as a resource, and if a deadlock occurs, it can be resolved if one car backs up. Several cars may have to be backed up if a deadlock occurs. In this, the starvation is possible. In the further slides, I will to tell you what is starvation. Firstly, a system consists of a finite number of resources to be distributed among a number of competing processes. The resources are partitioned into several types and each consisting of some of the number identical instances. Memory space, CPU cycle, files, input-output devices like printers and bus drives are examples of resource type. If a process requests an instance of a resource type, the allocation of any instance of a type will satisfy the request. And if it will not, that instance are not identical and the resource type classes have not been defined properly. So, under the normal operation, a process may utilize a resource in only one following sequence. That is, it can first request, then use, and then release. In the request, if request cannot be granted immediately, then the requesting process must wait until it can acquire the resource. In use, the process can operate on the resource, and in release, the process releases the resource. A set of processes in a deadlock state when every process in the set is waiting for an event that can be caused only by another process in the set. And the events with which we are mainly concerned here are resource acquisition and release, and the resources may be either a physical resources or a logical resources. Logical resources means files, semaphores, monitors, etc. Next is deadlock characterization. In a deadlock, the processes never finish executing and system resources are tied up, preventing other jobs from starting. The features that characterize deadlocks are that is the basic necessary conditions are following four conditions are. First is mutual exclusion. Mutual exclusion, at least one resource must be held in a non-shareable mode. That is, only one process at a time can use the resource. If another process requests that resource, the requesting process must be delayed until the resource has been released. Hold and wait, the next necessary condition. A process must be holding at least one resource and waiting to acquire additional resources that are currently being held by other processes. Next necessary condition is no preemption. Resources cannot be preempted. That is, a resource can be released only voluntarily by the process holding it. After that process can be completed its task. Circular wait, a set of processes like P0, P1, P2, and so on till Pn of waiting processes must exist such that P0 is waiting for a resource type held by P1, P1 is waiting for a resource held by P2, till so on is waiting for a resource by Pn, and Pn is waiting for a resource held by P0. We emphasize that all four conditions must hold for a deadlock to occur. The circular wait condition implies the hold and wait condition. So the four conditions are not completely independent. Next is a resource allocation graph. Deadlocks can be described more precisely in terms of a directed graph called a system resource allocation graph. This graph consists of a set of vertices V and a set of edges E. The set of vertices V is partitioned into two different types of nodes, that is P and R. P is basically the set consisting of all the active processes in the system, and R is basically the set consisting of all the resource types in the system. A directed edge from a process Pi to resource type Rj is denoted by Pi tends to Rj. It signifies that Pi has requested an instance of a resource type Rj and is currently waiting for that resource. And a directed edge from a resource type Rj to Pi is denoted by Rj tends to Pi. It signifies that an instance of a resource type Rj has been allocated to a process Pi. Here, a directed edge Pi tends to Rj is called request edge, and a directed edge Rj tends to Pi is called an assignment edge. Like in this particular circle represents a process, square represents a resource, and this dots represents the instances of a resource. For the request edge, the arrow will be from process to resource, and for the assignment edge, the arrow will be from the resource to process. This in particular square, we can see for a particular resource R1 or R2, whatever the initialization we are going to give to the resource, we have that particular resource having a 4 instances of that resource. By this example, we can see we have 3 processes P1, P2, P3 and 4 resources R1, R2, R3, R4. R1 consists of one single instance of a resource, R2 has 2 instances, R3 has 1 single instance, and R4 has 3 instances. Firstly, we understand which type of an edges we have been talking. As again, I am repeating, if the edge is from process to resource, it means it is being requesting for this resource, and if the instance is from resource to process, then it is an assignment edge. So we can see by firstly we are going to define what the processes are being holding and for what resource the process is being waiting. For the particular process P1, we can see R2 instance is already being allocated to process P1, but still process P1 is waiting for an R1 instance. For the P2, we can see the R2 instance is already being allocated to P2. R1 instance is also being allocated to P2, but it is being waiting for R3 instances. In P3, we can see that single instance of an R3 is being already assigned to P3. So if each resource has exactly one instance, then the cycle implies that the deadlock has occurred. But if the cycle involves only a set of resource type, each of which has only one single instance, then a deadlock has occurred, and each process involved in the cycle is deadlock. If a resource allocation graph does not have a cycle, then the system is not in a deadlock state. If there is a cycle, then the system may or may not be in a deadlock state. As I'm telling about the cycle, we check is there any cycle exists in this example or not. Starting from P1 to R1, R1 to P2, P2 to R3, R3 to P3, P3 to R2, and R2 to P1. Obviously, there is a cycle. Why there is a cycle? Because P1 is just waiting because of P2. If P2 releases the instance R1, then P1 will going to be assigned with that instance. Why P2B is being is the part of the cycle? Because P2 is waiting for an instance R3, which is already being assigned to P3. Why is P3 is being waiting for some of the instance? Definitely P3 is waiting for the instance R2. what is the next type of a cycle? Next type of a cycle is P2, R3, P3, R2, P1. In this example, it is another example. Here we can see P1. P1 is being allocated with the instance R2, but it is being waiting for the instance R1. For the P2, P2 requires only a single instance of R1, so it is already being allocated to R1, P2. P3 is already assigned with the instance of R1, but waiting for the R2. P4 is being already being assigned to the instance R2. Is there any deadlock? No, there is no deadlock. Why? Because if the P4 releases its instance of a R2, then it can be allocated to P3. So again, I repeat, if a resource allocation graph does not have a cycle, then the system is not in the deadlock state. But if there is a cycle, then the system may or may not be in deadlock state. Yeah. If graph contains no cycle, no deadlock. If graph contains cycle, if only one instance per resource type, then deadlock. If several instances per resource type, possibility of deadlock. These are the 4 key points which we have to always be remembering. No cycle means no deadlock. A cycle in a graph does not mean always it will be a deadlock. If we are having a single instance, then it can be a deadlock. But if we are having a several instances, then there may be a possibility of deadlock or not a deadlock. Thank you.